Okay, so we'll start looking at Pierce terminals and also what we call cup terminals. So Pierce terminals, these come in several setups. The one that we're going to be using looks like these. So one end is where we would mount this onto a terminal board. Okay with the terminal board, right? And this is where we solder in on this side right here. So this is where we're going to connect our conductor into the Pierce terminals. And these come in several ways. Also be considered Pierce terminal. So this is a quick disconnect socket right here. It's a female socket that we would plug a male plug into, and then on the back of it, this is where we actually connect the conductors at. Let y'all look at that, and let y'all actually grade some of these that was done last class. See what we're doing wrong, or see what they're doing. So what we're going to do is we'll start off by, when we start dealing with these terminals, the first thing we're going to do is we're going to pre-tin the conductor section. Take it and strip a certain amount of insulation off of it, and then we're going to pre-tin the conductor. Y'all understand what that means? What's tin? You solder, we use the term tin. What is that? Last day. This is what we coat something solid. Okay. We're going to be dealing with stranded conductors, which are the ones that are most often soldered. So we're going to have to, if we don't pre-tin a stranded conductor, it's what happens when we try to get a good tight connection to what we call bird cage. What's bird cage? That's the wires coming out of the power line. What we're going to do is we're going to pre-tin these and make them real easy to work with around the terminal, and then also it means less solder we'll have to use in our final connection. We're going to hook the tin conductor, strip the conductor. We're going to tin the conductor, which should be on here. We're going to hook the pre-tin conductor correctly, not have an overlap or anything like that. Then we're going to cinch it down. Cinch it down means what we're trying to do is we're trying to make the solder make the electrical connection. We want the devices to make the physical connection. So we don't want the solder being the only physical component that's holding our conductors together. So when we look at splicing wires, we never just lay them on top of each other. It's all, we're going to twist them together and do stuff like that and get a good block, get a good mechanical connection, and then let the solder provide the electrical connection. So the wire must be, the wire may approach from the top or the bottom. Okay? It says we're going to pre-hook the conductor. So we put the conductor in a hook, right? You understand? And then what are we going to do? We're going to push the hook through, and then we're going to cinch it down or tighten it down with the needle. In fact, this is a little different. So specifications shall not allow shorting between adjacent terminals. The clearance between the insulator and the actual terminal itself must be within what? 2 wire diameters. Y'all understand that? Not conductor diameter, wire diameter. Y'all understand the difference? Conductor would consist of the wire plus the insulation, right? Understand that? So we're talking about the actual diameter of the wire itself. I'll strip off one and I'll lay it up there, and that jacket must be within 2 wire gauges or 2 conductor gauges. And the insulation can't do what? Must not be covered with solder. So y'all understand the specs on this thing. Okay? So this is any Pierce terminal that we get into. This is the way, so this is what we mean by cinching down. It's over here on the right hand side. So what we're going to do is we're going to wrap this around and we're going to cinch it down right on the thing. What else does it say? The wires cannot overlap. Does it say that? So what that means is I can't come over here and wrap this thing around. I'm going to have to draw with this, guys. I'm sorry. I don't like drawing this because I can't adjust the gauge. So the wire cannot come around and overlap. It's got to be at least 180 degrees. Y'all understand? And of course, it can't stick up here in the air. This has to be within what? Yeah, these have to be within 2 wire gauges. Got to have at least what? This says at least 90. Normally what I like is 180. We don't let this stick up in the air. This is within 2 wire gauges. We never let the wires do what? Overlap. I understand that. And we'll look at some of these. So this don't meet that, this don't meet it, this don't meet it. This is a bad joint. This is the closest one, and this is awful. So this is the method they're showing coming in from the top. They're showing it to bend it in a what? Bend it in an L shape. Then we can do what? Bring it through, wrap it around, check your what? I mean, this is the time you're gonna check your insulation clearance before you set that. Okay? You can unbend it and get it back if you got it too long. Do that if you get it too short. So there's real no excuse of not meeting that 2 diameter, maximum 2 now, which means it can be closer, but it can't be close, right? Y'all understand that? Y'all understand? So this is one that method, and then of course what they do in here is they're clipping off the excess. And then they're going to cinch it down, which means we want this to be what? We want that conductor to be touching the terminal on these 2 sides. This is what we call a turret that we run into a lot on printed circuit boards. In fact, I should pass it. We can call it turret. We can put multiple conductors on this. Another thing that we need to remember is that, of course, here we're not going to have to do that because we're going to be soldering little pieces of wire. But we talked about this in the other class. When you bring in a cable or a conductor, you always want to be what we call strangle, right? We never make the wire high. We always leave a loop or something like that. Line that. So the wire will break. What's going to happen is they expand and go down to they contract. And if they contract enough to completely break the conductor. But if you got a strain leak in there, so if you go out to your car and you look at all the electrical conductors, when they come off a wall and go through the permanent, they all look out all your cables, all your pipes and stuff are not tight in order to get out of the wall. And the metal ones are tight, flexible ones, they always leave a loop because they know the vibration of the engine and all that kind of stuff. This is a good job. So what we're looking for is we need to still see the conductor. Can y'all see this? We still need to see the conductor. We need to we can see the strands in the conductor. we have this thing that we refer to as a fillet. And what we're looking for is, if I was to look at this from the side, I could see my conductor, and then this would be the terminal. And what we're looking for is this thing to come up and the solder to look like this. Understand what I'm saying? So you can literally see the conductor. Now, why do we want to do that? Well, what we want to do is we want to see what we call a wedding. Now, wedding is where molecules of solder are actually adhere to the surface molecules of the metal we're trying to solder together. If you cover that thing up, you cannot see the wedding. And if I can't see that this is a good solder joint, I assume it's what bad. Even though it might be electrically perfect, right? You understand? We don't know it's good. We assume it's what? It's bad. And just because it reads 0 ohms of an ohm meter, it probably would. What we're trying to do is set up a junction that will last forever, right? You understand that? But what happens if you can't see it, it's a bad joint. After a while, the wire will start oxidizing and start floating and pushing, and eventually that connection that originally checked 0 ohms is going to be acting like an open. If it's not acting like an open, it's going to act like a non-resistor. If it acts like a resistor, then it's going to drop the voltage, right? If it drops the voltage, it's going to get hot, right? If it gets hot, what happens? The copper gets hot, it oxidizes, and then it just avalanches. If the conductor gets hot, it can literally turn off the insulation and make the insulation move brittle. If the insulation comes off the wire, then you got short circuits and plate happen, right? So if you make a really good joint or termination, then this guy here will last forever unless somebody comes in and cuts it off. At least 90 degrees, wire must not overlap. The wire or conductor must be visible through the solder. Y'all understand? So that's a good job. Dang, I'm gonna have to find the PowerPoints. So the one on the left doesn't have enough solder on it. The one in the center is good, and the one on the right has too much solder. So that's the biggest problem we have with people controlling their solder. Now, if you get too much solder on that, what you can do is clean off. One thing you can do is clean off the tip of the iron real good. Get the tin, not all of it, and then touch it with your iron and let the solder wick up onto the solder. If it gets too bad, then what we can do, I forgot my box, is we can use something called a solder bag. Basically, it's a little pump thing. Let me go get that before they start over here. I won't be able to get it. I had it propped open, but I'll unlock it. I had it propped open, but somebody came by and unpropped it. This is a device called a solder bag. And if you're into this kind of stuff, this would be a tool that you need. You can get them different sizes. I prefer the plastic ones. They make them in metal, but what happens on the metal is that the solder will get into the threads, and eventually they'll strip out. These guys basically are pretty easy to take apart. So you have to clean them often. Petroleum jelly to keep your seal right here nice and smooth. Keep it cleaned down. What it's got a Teflon tip on it. Teflon has an extremely high melting temperature, so we don't have to worry about the tip melting when we get up against our soldering iron. And basically, all you do is just cock it, and then put it, get your solder melted, and when it turns into a liquid, just press the button. Put this up directly up against the iron and the solder. You want to leave the iron on there. You see people, solder cools off real fast. Solder basically goes from a liquid to a solid in almost no time, right? As soon as you move your iron off there, we're talking about a second or two, that solder will solve. Now the problem is, I see people do all this, they'll try to heat up the solder with their iron. They'll try to pull the iron out. They'll try to get the solder back into the solder before it does what? Before it turns solid. And that's high probability. These guys are designed to be put down on top of your iron. So you hook that sucker up, you leave your iron on there, you push it down, hit the button, sucks all the motion solid up. As soon as you feel it move. These are called solder packs. Some people call them solder suckers, but they don't have that name. So we're going to be doing these. We're going to strip the wire. We're going to pre-tin it. Everybody understand pre-tin? What we're going to do, we're going to coat that wire with a piece of solder, that stranded wire with some solder. Then we can do what? You can get any way you want to. One bird cage, cinch it down a little bit, and then we can solder. It takes very little solder now. These are the actual cup solder. So when we deal with connectors, especially solder connectors, crimp pins are okay, but crimp connectors, which we'll deal with next, always has the problem of not being crimped correctly and not being easily the wire will lap. Solder, though, you can see. So a lot of our conductors, a lot of our connectors use what we call solder pins, and these are what we call cup pins if it focuses, because the back where we're going to actually do our soldering is in the shape of a cup. And then, of course, the pin would insert into a connector. And that's what these little ridges are. So you can solder it outside the connector, and you push it in and snap into a little clamp in there that holds the pin in the connector itself. So we call it, I'm not going to tell you how many of those things are. I've been in a lot of companies where you actually have to make your tables. They use standard connectors, but the wiring of the cables that you buy standards like the RS-232 or PokeBus or something like that, and that might not be the way you want your cable made, right? So you can buy a lot of standard connectors, and that's what we do. Because if we buy standard connectors, then that means there's going to be a male and a female counterpart. Y'all understand male and female? Yes. This would be what we call a female connector. NEC calls these R's. So when I look at these wall plugs over here, like that wall plug over there, that's a NEMA 20R. That means it's the receptor. The plug that's designed to go into that would be a NEMA 20P. So that's what you do. So that means standardized connector, then I can buy the R, while we can do what? That would be what we call a female. And then the guy that's going to be in the and I know that is probably sexist, but that is the truth. So the female connector has the hose that the pins plug into. So we call them gender roles. So when you order them, that's what you got to do. Well, if you got a DB9, R, then a DB9P would be the plug that plugs in. Right? Some connectors, like Molex connectors, you decide the gender of the plugs. So what's nice about Molex is you might have you get a standard shell, and then you decide how to hook the pins in there. You might have one female, one male, one female. You decide how to set up for your cables. And I've dealt with a bunch of those. Molex connectors are very, very popular in automobiles. These little plastic connectors like this. These are very popular in automobiles. If you look up under your dashboard, you'll see a few of these Molex connectors. And the pins go in here, and you decide whether you're going to use a female or you decide whether it's going to be a male. Those are crimp connectors, by the way. So those will be the ones that we work with. Next. So we'll start off with soldering. So we call these cup connectors. Y'all saw it right. We call it cup terminals. These are used inside connectors. This would go in the male connector. And of course, this is a DB25, which is a standard connector. For years, it was a standard connector that was on the back of the computer. So if we went into a computer lab over there and slid it out, we'd see one of these DB25 connectors. It would be a film. Y'all took the intro to robotics. That was the connector with the gray robot. And off the DB25 cable. So what we do first of all is we make sure we pre-tin the conductor. Are you okay? We pre-tin the conductor. And what we do is we practice fit the conductor into the cup, making sure that our insulation is within what? 2 diameters. Of course, here you're in total control of that. It's not when it gets down and touches, that's going to be illegal because that means the solder is going to come up and touch you. You want that to happen, right? So you want it to be 2 conductors. One would be great. But you're controlling that, right? Well, if it's too long, what can you do? You cut it off, right? If it's too short, what can you do? You can strip off a little more than finish, right? And you're in total control of these. You don't have to hook these. We don't have flux, by the way. The flux is in the solder. So that's what they're doing. They're putting solder. So what we do, let's see if they show us a little better. So what we do is we tin our iron. We come up here and fill the cup. We don't fill it, probably around 2/3 full. Then what do? We heat it up with our iron. We stick our wire into it. Then what we do is we pull it forward to make sure we get solder in behind it. Then we push it forward. Then we push it. And then we take the iron off and hold the wire until solidified. You understand that? They got to do that. They even try. By the way, we have what we call third hands that we use in soldering. So, you can't hold this thing. This thing is gold plated. It's copper gold plated. Gold is an extremely good conductor feed. So don't try to hold the pin while you solder. They're going to burn it. So we use a third hand to hold these. Third hand. Somebody picked the alligator. So usually with alligator on. In fact, it might be tomorrow. So it's got a little alligator clip on there, and you can clip these terminals into that thing when you do your soldering instead of holding them in your hands. So what we're trying to do here is, of course, we want to see this, what we call this fillet, right? You understand? The front should look similar to this. If it comes up here and bulges out like that, what does that mean? That's too much solder, right? You understand that? Okay. The wire must be inserted to the bottom of the cup, tilting the wire forward and back while soldering. Solder shall fill 75% of the cup. Surface fillet must form between the wire and the terminal. Wire must have stress relief. Like I said, we're not going to have stress relief because we're just going to be doing a little small piece of wire. But out there, you need to remember when you do that, you need to have stress relief inside there. Insulation must be less than, don't say equal to, here does it say? It says less than what? 2 wire diameters from the top of the terminal. Understand that? And of course, this is what we're grading on. So the one on the left, the wire's not completely inserted, plus they don't have enough solder. The one in the middle is perfect. The one on the right's got too much solder. And the biggest problem we have is people controlling their solder. So what we do is you'll find people that use extremely big gauge solder. What we like to use is 30 gauge solder. I think it's 30. But it's a real thin gauge solder. Now remember, solder has lead in it, right? So what are y'all going to do? You're not going to put this in your mouth, right? If you got any cuts on your hands, we'll have to go get you a Band-Aid. You need to put a Band-Aid on your finger. Because what will happen? It'll go through and get into your knee. That's the way it gets in there. The only way solder can get into your bloodstream and get into your body is once you put it in your mouth or you ingest it. And that's what their big thing they talk about. People used to latex paint to make it adhere real good. So that's the big thing now. All our paint now is free, but you get into the older parts of the old house, and there's a high likelihood that the paint is going to have lead in it. You really watch that, start killing and stuff like that, especially if you got kids. Kids put in, and they get up right 1, 2, 3 years old, they pick it in their hand. So what you need to do, if you got any cuts on your hands, if you don't have cuts on your hands, don't worry about it. But what we need to do is before we solder, we need to do what? We need to wash our hands, go in there in the room, don't use the sanitize, this bacterial stuff they got on the wall. That's not going to sanitize the solid, it's not going to get rid of the solid. So when you get through today, what you make sure you do, make sure you go and wash your hands before we leave. When you hand in the solder and you scratch your nose, don't you? Yeah, because that's another way. So that's Pierce terminals. What else we got? We got Pierce terminals. We got turret. We got the turret. We have the bifurcated terminals that we're also going to work with. So let me bring those up real quick. And I've lost my blackboard. I'll start it back up. So these are bifurcated terminals. By the way, if you do a turret terminal, and you can do multiple conductors on a turret terminal, and that slide didn't show it. And I don't have these labels. I'll have to find it. These are the actual PowerPoints. The PowerPoints themselves are really, really long, so we split them into terminals. We're looking at stripping, right? Showed y'all the strippers. These guys right here. Everybody okay there? And what do you do right off the mat? You got an outline. some that are critical. Here's another set that's real popular too. What you do on this one to set your gauge is you have a little turn wheel on it. Here's your stripper right here. And then what you do is you turn this thing to set your gauge. And what this does is it prevents it from turning past the gauge. And then you also have the one that locks it closed so the sharp edge won't be away. Of course, what most people do is they'll put it on the biggest gauge, like 12 gauge wire. Not 12 gauge. They'll put it on the smallest gauge. And then they have problems because, you understand that, and I've seen people actually take this thing off, which is not good. So this is another set of strippers that's pretty common. So if the wire is real easy to strip, that means you chose the wrong gauge. If you're not cutting through these, why what you're doing, you're a little breaking. So if you twist that thing around, that might describe those conductors, what's going to happen. Solid conductors, stranded conductor, what's going to happen is some strands. Now, some of your strands break off. What's the problem with that? You're changing the gauge on the wire. We gave you all a little chart of the allowable strips on that. So let's see if we can find the right PowerPoint. So this is 2. Let's see what 2 covers. Come on. We got the Chromius network on this campus. And that's being recorded too. I can log on at 1 o'clock in the morning. I'll get a network busy. Maybe this is the whole thing. Oh yeah, we talked about strands, allowable strands. Strippers, we have an electric stripper over there. I didn't go get it. What's nice about electric strippers, these are heat strippers, and what's nice about those is there's no way in the world you can get water. What they do is they do melt insulation off. We got it set over there. I showed y'all these guys right here, right? I don't know if I brought them over or not. Let's see. Okay, so this is the turret, and then what we're going to do is we're going to pre-pin and form the wire, right? I understand that. So what you do is you just basically take your Nelos pliers, put it in there where you want it, and you bend the wire around the Nelos pliers. Then we want to make sure what? We want to make sure that the conductor is flat against the surface. We want to make sure that the is within. So it don't say it needs to be, when it says within, what does that mean? It means it's got to be less than 2 diameter. Y'all understand that? Okay. It says conductor must wrap at least what? 180 degrees, and it don't say that, but you don't want it to do overlap. Everybody understand that? Okay. Shall not overlap. Minimum of what? Minimum of what? Minimum wrap of what? 180, right? Now, if we put more than one, so we don't want to leave anything sticking out because that'll cause short circuits. If we put more than one, then we stack them on top of each other. If they're gauges, then if you use different gauge wire, then the biggest gauge goes for the bottom. The biggest wire size goes for the bottom, which would be the small gauge, right? Okay. When I use the term a bigger gauge, I'm talking about a bigger wire. The bigger gauge wire has a smaller gauge number. So you get those numbers in the actual gauge of the wire. Don't get those confused with each other. So what we do is we come up here, where do we end up? We wrap it around, we cinch it down, we make sure we have strain relief. And where do we solder? We clean our iron. Where do we solder at? Where are we going to put our solder at? On the opposite side of the iron. We're going to tin the iron. What are we going to tin the iron for? So to get heat transfer, right? You understand that. A little bubble of a solder on your iron. Bring it over, touch that against there. Then we're going to end up soldering. You might have to do this. So if you touch it on the opposite side and the solder does not flow, then come over there on your iron, the junction of the iron and wire, and put a little dab of salt. Everybody understand that? But you're always going to end up soldering where? Always end up soldering on the opposite side of the iron. And every once in a while what will happen is you don't get a good tin, or the solder wicks out real fast when you get on those stranded wires. Then you don't get good heat transfer. Or what you can do with the iron on there is you can touch it right at that junction on the iron and the wire, and then take it off. As soon as you see it, the solder starts filling in the wire. Do what? Move the solder over to the other side. So always end up soldering where? On the opposite side of the iron. Everybody okay there? This is what they're talking about. Different gauge wires. Move the soldering iron. So that's a good job. So notice, can y'all see this? You can actually see the what? You can still see the strands of the wire, right? Of the stranded wire. You can see the fillet right here where it comes in and bonds with this. You can see the fillet down here where it comes in and bonds with the actual turret itself. This one's not enough solder. This one's a good job, and this over here is too much. So here we can't see the wire. If you can't see the conductor, if you can't see that wedding, then you assume it's what? It's bad, right? This is the bifurcated terminal that we just passed around. These things are really neat. So what's insulation clearance is within what? 2 wire gauges. Pre-tin the conductor. You're going to wrap it around there, right? You're not going to allow it. You can wrap it a minimum of 90 degrees. If you wrap it more, you cannot let it do what? So this is the minimum route. I can't get in front of it anymore. This is the minimum route, but you can wrap it, and all you're going to do is not let it what? Overlap. We're not going to flux these things. These things are pretty clean. We're going to make sure that the conductor is in contact on the bottom and wraps around. Minimum 90 degrees. We're going to cinch it down, generally squeeze the end of the wire tightly until it don't damage the strands. We see people really get on those things. Wire must be flat against the base. Conductor route must be 90 degrees minimum. Insulation must be within 2 wire sizes. Are we okay there? Multiple wires, you see how we can do that? Now, if you probably noticed, this guy here is hollow. So what you can actually do is you can actually bring the conductor up through it, if they show that. So these are different ways we could do it. We could wrap it. These are alternate connections. If the wire gauge just fits, you can bring it down to the 2. If it's small, you can do what? You can put it in a hook, or you can make sure it's up against the side. Another method we can do is, let's see if they show that. No, they don't show it. The bifurcated terminal, I think, is actually hollow. So another method I've seen used is they bring the insulator, actually bring the insulator up through it. I thought it was in that slide, but it wasn't. This is the bottom. Can you see the hole? And then if we look at the top, what do we see? Oops. Get this. See the hole coming through the top. So we can actually bring the conductor up through here, up through the bifurcated terminal, and then bring it and wrap it and solder it. I've seen that too, especially when you're trying to bring a conductor in from the opposite side of the circuit card. So this actually solders onto something on the circuit card right here, which is the same thing with the bifurcated terminals. I've got some circuit cards over there that's got terminals on it like that. But like I said, I won't be able to get over there now. Of course, what we're going to do, this is the same thing. We're going to, we might have to touch the iron on this side if the solder doesn't flow. We're always going to end up what? Soldering on the other side, away from the iron. Everybody understand that? What I was looking for is, so that's basically all our terminals. So we got Pierce terminal. We got what they call a hook terminal, which was next on the slides. It's still up there. Not that one, Rich. But this is a hook terminal. It's basically all these follow the same procedure. So what are you going to do with this guy? You're going to do what? You're going to pre-tin your wire. Then what are you going to do? Then you're going to hook it you're going to put it in a hoop. Then what you're going to do? You're going to wrap it around. Understand? You're going to verify, when you hook it around, you're going to verify that the insulator is within what? 2 wire diameters. You're going to do at least 180 degrees, right? But you're not going to let the wires do what? Overlap. That makes sense. So every one of these are the same. And I'm trying to see where we actually do y'all go ahead and take a break. We might just do this in class. I have no idea where the slides are at. I'll show y'all how to splice these things.